My name is Omani Wale Salami. I'm presenting our paper titled Past Event Record Test for Mitigating Session Hijacking and Cross-Site Request Forgery. This is the outline of our presentation. There are some attacks that are used to mislead computer in order to steal important information. Among these attacks is session hijacking and the cross-site request forgery attack. Session hijack attacks is an attack in which the attacker replace one of the parties in the session and put himself in place of that party. IP spoofing attack can be used to implement session hijack attack by create a similar packet that is similar to the original session packet and deceive one of the party in the session. Cross-site request forgery attack can also be used to implement session hijack attack by putting a script on the victim system. The script will be sending important information to the attacker. From there, attacker can get information which he can use to hijack the session and replace one of the original parties in the session by itself. There is simply a use of computer for sharing sensitive information. Therefore, there is need to make the online transaction safer. Different solutions have been proposed by different researchers to mitigate the session hijack attacks and make online transactions safer. Among the solutions proposed are encrypted strong session ID, using intelligence system for site risk rating, and using machine learning for detecting vulnerability in web application. The danger of losing important information to an attacker who might have tricked the computer to wrongly directed the unintended information to the attacker require that audience be ascertained before they forward the information to it. This, our solution proposed to offer a solution that periodically check recipient of information to be and be sure that it is the legitimate user in a computer session. This solution proposes a solution that periodically check recipient of information to be the legitimate one in a computer session. We use time traveling concept in which past event is reviewed to identify known counterpart and check available record of previous experience with it to accept or reject a transaction based on the assessment of past experience, whether it was successful or was not a successful experience. It is assumed that the original party in the computer session register with each other. They also share a token that we call no-party verification tokens, which are used in this solution for verifying each party in the transaction. NS3 test bench was used for the prototype of this solution. Elliptic curve cryptography parameters were used with Crypto++ for security implementation. Here is the flow chart of the steps involve a registration for our proposed solution. There are two users we call FRT member A, which is the client, and FRT member B, which is the server. So the two users share elliptic feed parameters, which include the feed type, the basic point generator, and other necessary parameters that are used to compute the security keys like public key and the private key, and also create identity certificates. After sharing the necessary parameter and creation of the keys, the member in the transaction share the identity and the certificate as may be necessary. So during this process, when client A sends its request to server B, Server B will now generate a number of no-party verification tokens and send it to the client A. When client A receives this no-party verification token, it will generate its own token as well, which will be different from those ones that are generated by the server, and send it back to the server. The client will append those tokens that it received from the server. It will append it to the one it generated and save it with itself. And the server will prepare those tokens that it received from the client. It will prepare it to the one it generated and save it to itself. This is necessary so that the tokens will have the same serial number on both ends, both the client and server end. When there is need for verification, if client A sent a transaction request to server B will now check from the no-party verification token that it saved with the identity that client A submitted. It will now encrypt one, it will select one of the tokens and encrypt it. It will encrypt the index number of that token. It will encrypt the index number of that token inside the list. It will now take a fraction of the characters of the hash of the token. It will now concatenate it together with the full length of the hash of the serial number and separate the two by a delimiter. It will now send the concatenated characters to the client. Client A will now receive the character string. Look for the delimiter and separate them to two. It will look for the one that have full hash block length. It will take that as the serial number and check among the serial number in the list of a token that it has, which one match the one sent. It will pick that serial number and take the token at that serial number. It will now generate the hash of the token at that serial number, compare it with the fraction of the token hash character that the server sent. If it sees a match at any part of the token that the client generated, either from the middle to this edge, or from beginning to the middle, or from any part of the token hash that it generated. If it see a match, it will now see that it will take it that's the token that the server created the hash and send a fraction of the hash to it and send the full fraction. It will send the full hash back to the server. When the server receives the hash, it will now compare it with the hash of the token that it earlier sent to the client. If they match, it will use that to verify that the client is the original client that registered the identity. The prototype of this solution was tested against identity theft and spoofing attack. We assume that the attacker does not have access to the path parameters, which is the no-party verification tokens that they are using to verify each other. Identity theft is assumed. We assume in the identity theft that the attacker stole the identity parameter using a script that was installed on the victim system. The script was the one that directed the necessary information that enabled the attacker to get the identity of the user. In spoofing attack, we are assuming that the attacker successfully produced transaction message packets. We compare our solution with OKAMO proposed by SessionHijacking and Triparty 2019, and also the solution titled Secure Model for SessionHijacking using Hashing Algorithm proposed by Tucker and Fagel 2018. Here we call the solution of Tucker and Fagel 2018, we call it Secure Model for search. OKAMO prefers cross-site request forgery, where Secure Model prefers session hijacking, but our solution prevents hijacker from receiving information that is not due to it by throwing a challenge to the attacker. If attacker failed the challenge, information that it requests will not be sent to it. Otherwise, if it passed their challenge, then the information will be sent to it. We tested the rate of detection by each solution, which measure how fast the solution runs on the system. The rate of detection is tested per second. The graph below shows the result of the result for each solution. The blue color shows the result for Kukiyama, which took the longest time, while the brown color shows the result for our solution, the PET solution, which follow, and the gray color shows the time taken by the secure model. Secure model was the fastest because it only go through its data. When it receives an ID, it only generate the hash of the ID and compare it with the hashes that it has in the database. This is faster, but our solution involve creation of hash, and also it involve encryption and decryption, which make it slower than secure model. Kukiyama is slower than all other solutions because it involves deep packet sniffing, whereby it sniff every packet that it receives to get the parameter that is needed for its security solution. We also tested for false positive detection, which shows the number of attack requests that each solution take to the original request. We calculate we add up all the false positive detection that each solution generated throughout the simulation. We run 100 solution. We run 100 simulation. The simulation will run on 100 times, and the number of false positive detection obtained for all the 100 times were summed up together and divided by 100 to get the average. We now deduct this average from 100 to get the average accurate detection that each solution was able to get. Secure model was able to get 4 accurate detection under identity theft. Kukiyama was able to get 87, and our solution, PET solution, was able to get 97 under identity theft. Also, under spoofing attack, secure model was only able to detect 3 correctly. Kukiyama was able to detect 56 correctly, while our solution detected 97 correctly. In conclusion, this research presupposed a solution that used previous event record test, which we call PAT, PRT for short, to identify non-trusted user. Token share at the beginning, there's no party verification token. At the beginning, token share at the beginning of a session are used for continuous confirmation of the party. On the other hand, it prevents identity theft and other impostor by using the test to confirm it if the attacker is the original client that actually registered the identity. Also, cross-site request forgery is prevented by confirming if the client that the request was directed to is actually the one that the session was established with. In any case, when foul play is suspected, the transaction is stopped. Thank you for listening.